can you see my screen?
Yes, yes, visible.
Yeah. Okay, so first let's recall what you saw in this week. So the first thing that you saw was the Becker-Gill-Solvay theorem. So can you tell me what the theorem is?
So this theorem says that P is equal to NP or P is not equals to NP cannot be inferred through diagonalization.
Right.
Yeah.
Yeah, so the exact statement is that there exists oracles A and B such that P to the A equals to NP to the A and P to the B not equals to NP to the B. Now, as you said, this implies that you can't use diagonalization to resolve P versus NP, and that's because diagonalization itself relativizes. That is, if you can prove something using diagonalization for ordinary Turing machines, you can prove the exact same thing for oracle Turing machines. So now, since we know that there exist two oracles for which you get two different conclusions, you can't prove either of these conclusions, that is P equals to NP or P not equals to NP, using diagonalization, because that would contradict the other statement.
So,
Yeah.
so this statement is not that much clear to me. Say, if we consider two complexity classes, say C1 and C2,
Okay.
so does this mean that if C1 is contained there in C2, so then C1A would always be there in C2?
Hello.
Yeah.
Yeah,
So
I lost you for a while.
am I audible?
Yeah, now you're audible.
Okay, so my query is that if C1 is contained there in C2, so does this mean that C1A would always be there, would always be a subset of the C2A?
Mm, wait. Yes, because so what does it mean to say that C is in C1 is in C2, right? Every language in C1 is also in C2. So, for example, if you have a Turing machine for the okay, so yeah, so the classes have to be sort of like somewhat well behaved. For example, if both are time classes or both are space classes, something like that, then you should be fine. So basically, what you should be able to do is pick a Turing machine that decides the C language in C1. That should be an
Hmm.
acceptable Turing machine for C2.
Okay.
Maybe you can create some pathological classes.
Hmm.
Yeah, I'm not sure about that, but if you can pick a Turing machine from C1 and
Hmm.
that's also a Turing machine for C2, then it's fine.
Okay.
Yeah.
So okay. So what is the real importance of the Baker-Gill-Soloway theorem then?
Okay, so the real importance is sort of a negative result. So it
Hmm.
tells us the following: if we want to prove P, if you are trying to prove P not equals to NP or P equals to NP, stop using
Hmm.
diagonalization. You won't get there using diagonalization.
Okay.
Yeah, so it's one of the things called barrier results. So
Hmm.
proves that for a certain technique, in this case diagonalization, there is a barrier
Hmm.
that won't allow you to get where you want. Yeah.
Right. So, because P is there inside NP,
Hmm.
P is a subset of NP. So, does it mean won't it infer that P A would always be equals to or would always be the subset of the NPA?
Yes, because okay, so when is a language in P to the A, there exists a deterministic Turing machine, which when given
Hmm.
oracle access to A,
Hmm.
decides that language, right?
Yes,
But the
and in
exact
fact, PA would be same as P only, I think.
no, P with oracle access to A, right? So for example, A can be a very difficult problem, right?
Okay,
So for
okay.
example, something in X power X to the X or something like that.
Hmm.
Yeah,
Right, right.
yeah,
Yeah.
yeah,
All right. All
yeah. Okay, so and okay, so the thing is that Baker-Gill-Solvay theorem tells you that diagonalization cannot be. It gives you a weakness of diagonalization, right? But the
right.
interesting thing is its proof is also using diagonalization. So basically, you are using diagonalization to show that diagonalization is
Mhm.
not strong enough. That's interesting.
And how this diagonalization process in theory of computation is different from that diagonalization which we used to study in set theory. Uh,
They are okay. So the ideas are exactly the same. It's just that
Mm-hmm.
when you say in computation complexity, when you use the word diagonalization, or
Mm-hmm.
for example, when I over here I say that diagonalization cannot be used to prove P not equals to NP, I have something very specific in mind. In in particular, I say that a proof uh, uses diagonalization if it
Mm-hmm.
only relies on two things. Number one, uh, every Turing machine can be represented using strings, and number
Mm-hmm.
two, one Turing machine can simulate another Turing machine without too much blow up in time or space. So if a proof uses just these two things, then I would call it a diagonalization proof. So over here I've made it much more formal, but the
Mm-hmm.
essential idea is exactly the same.
Uh, okay, okay. So because I have issue with the name of this term, where
Okay,
do we find the diagonalization kind of this stuff there? Say if I'm executing the Turing machine on its own description, and then later on if I'm flipping the output and then reaching to the contradiction, then where is the I mean, where is the use of the term diagonal here? I mean, why do we call this process the diagonalization?
okay. So uh, what you are going to do is, so you are asking about that specific question of a Turing machine running on its own input, right?
That is what the meaning of the term diagonalization is,
Right.
as it was discussed in the class.
Wait. Okay. So in class, diagonalization was when a Turing machine executes itself.
Yes, so I mean the proof. I mean the way we prove that the Haltin problem is undecidable
Right.
is a typical example of the diagonalization process,
Right.
because we cannot compute everything. We cannot analyze every aspect of the computation through the computation itself.
Right.
So in that way.
Right. So I think the reason it's called diagonalization is if you put all the Turing machines on the right. So basically, you can draw this table where the rows and columns are both labeled by Turing machines,
Mm-hmm.
and we basically make every Turing machine fail on its own encoding, right? So if you look at that table, the Turing machine exactly the string that Turing machine fails on falls in the diagonal of that table, right?
Yes, yes,
Right.
yes.
Yeah.
Probably
Right.
because of that.
Yeah.
Yeah. So now I've got some idea. Yeah.
Right.
Yeah. So you can continue the next
Yes.
thing. Yeah. True.
Okay. Yeah. So then you saw randomized complexity classes, and these classes, the classes that you saw were RP, QRP, BPP, and ZPP. Now, to define these classes, we use the notion of probabilistic Turing machine, or PTM, and it's defined as follows. So it's just like an NDTM in that it also has two transition functions. However, unlike NDTM, which chooses one of the two functions arbitrarily at every step, a probabilistic Turing machine chooses one of the two functions randomly. So a probabilistic Turing machine, basically you can think of it as follows. It tosses a fair coin. If it lands heads, it chooses one function. If it lands tails, it chooses another function. On the other hand, NDTM is not bound to toss a coin and follow the outcome of the coin. It can do anything it wants.
Yes.
Yeah, and we say that a PTM runs in polynomial time if on any input x in 0, 1 star, it halts in poly x time regardless of its random choices. So no matter what the random choices are, it should always halt in polynomial time.
Mhm.
Then you would have seen the definitions of the class RP. So RP is a class of all languages L such that there exists a polynomial time probabilistic Turing machine M satisfying these two conditions. X is in L implies probability that mx is equal to 1 is at least half, and x is not in L implies that probability mx equals to 1 is 0. Over here the probabilities are taken over the internal randomness of the Turing machine. So notice that uh, if M is a Turing machine for a language in the class RP, whenever it outputs 1, it is always correct, and whenever it outputs 0, it might be wrong. So this is a one-sided error class. and it's easy to show that P is contained in RP and RP is contained in NP. Then you would have seen the class CoRP, which is a class of all languages L, such that there exists a polynomial time probabilistic Turing machine M satisfying X is in L implies that probability Mx is equal to 1 is 1. Just a second, if someone wants to join. Yeah. So there exists a probabilistic Turing machine M satisfying X is in L implies probability M of X is equal to 1, and X is not in L implies probability Mx is equal to 1 is at most half. That is, probability Mx equals to 0 is at least half. So notice that a probabilistic Turing machine for CoRP, whenever it outputs 0, it is always correct. But whenever it outputs 1, it might be wrong. So because of this reason, this is also a one-sided error class. And you would have seen that P is all in CoRP and CoRP is in CoNP. And it's easy to show that L is in RP if and only if X complement is in CoRP. So that's why we have Co over here in the name. So these were like one-sided error classes. Then you would have seen a two-sided error class, BPP. So BPP is a class of all languages L such that there exists a polynomial time probabilistic Turing machine satisfying X is in L implies probability Mx equals to 1 is at least 2/3, and X is not in L implies probability Mx equals to 1 is at most 1/3. So over here, if a machine M is a machine for a BPP language, it can go wrong when it outputs 0 as well as it can go wrong when it outputs 1. So this is a two-sided error class. And you would have also have seen that P, RP and CoRP are in BPP. Then you saw the class ZPP. So one definition of ZPP is that it is a class of all languages L such that there exists a polynomial time PTM M which can output three things. So all the Turing machines that we saw till now outputted either 1 or 0, that is either accept or reject. Now it can also fail, but the condition is that the probability of failure is at most half, and whenever the Turing machine outputs 1, X is guaranteed to be in L, and whenever the Turing machine outputs 0, X is guaranteed to be not in L. So a machine in ZPP never errs. It can fail, so it can say, okay, I don't know what the answer is, but whenever it says, whenever it gives you the answer, it's always correct. And you saw that ZPP is equal to RP intersection CoRP. And there is an alternative definition for ZPP, and it is the following: it's a class of all languages L, such that there exists a PTM M satisfying X is in L implies Mx equals to 1, and X is not in L implies Mx equals to 0. So this Turing machine always outputs 1 and 0. It does not output fail. So it's like the Turing machines that we have been seeing up till now. Moreover, it never errs. So whenever it gives you the answer, it's always correct. But the caveat is that now the running time is no longer need not be polynomial in the size of X, but the expectation of the running time is polynomial in X. And again, the expectation is taken on the internal randomness of the Turing machine. And finally, you saw the notion of boosting, which is just that which is a trick to increase the success probability of a probabilistic Turing machine. And this is generally done using a concentration inequality called Chernoff bound. And you also saw Chernoff bounds and Markov inequality in the week. And what boosting tells you is that the following: the exact constants 1 over 2, 2 over 3, etc. in the definitions of RP, CoRP, and BPP and ZPP do not matter, and any reasonable constants or bounds over here would work. So if you are okay with the theory that was covered in this week, we can start with the problems. Okay, so if everyone is fine with the theory, we'll start with the first problem. Yeah, so the problem is the following: which of the following is implied by the Becker-Gill-Solovay theorem? The P versus NP equation cannot be resolved at all. The P versus NP equation cannot be resolved using diagonalization. The question cannot be resolved using reductions, and the question can only be resolved using randomization. This is just like a recall question. So yeah, what's the answer to this?
I think the answer is B.
Yeah,
P and NP cannot be resolved using diagonalization.
yes. So this is a recall question. There is nothing to explain over here. The same is true for the next question. So the Becker-Gill-Solovay theorem constructs two oracles. So in the proof, you construct two oracles, A and B, such that P to the A equals NP to the A and P to the B not equals to NP to the B. So which of the following is correct? Both the oracles are considered explicitly. Only oracle A is constructed explicitly, but oracle B is not considered explicitly. Oracle B is constructed explicitly, but not oracle A, and neither oracle is constructed explicitly. So what's the answer?
I think the answer is A, that both have to be constructed explicitly. I'm not sure because because I have not referred to the proof of this theorem, so I'm not sure. But I think that both should be constructed explicitly.
Okay, so the answer is actually B. A is considered explicitly, but B is not considered explicitly. You merely show that a B exists.
Okay.
Yeah. Okay, so let's look at the next problem. Consider a three-set instance where each clause consists of three distinct variables. Each variable is independently and randomly assigned either true or false, so that is either 1 or 0 with equal probability, so probability half. And what is the expected fraction of the clauses that will be satisfied? So is the question clear? Because this is slightly different than what we have been doing till now.
Yes.
Yeah.
So we have a three-set instance, and how many variables are there in the instance?
N.
N number of the
Right.
variable.
And what you do is you pick every variable, you toss a coin. If the coin lands heads, you toss a fair coin. If the coin lands heads up, you assign it 1 or true, and if it lands tail up, you assign it 0. And then you check how many clauses are satisfied. You take that number divided by the number of total clauses, and that's your answer.
Yes, and this three-set instance is there in the clausal form or not?
Yeah, so you are given it as a formula.
As a formula, not in the clausal form, say C1 and C2, wherein I only need to verify the truthfulness of only one clause. If one of, okay, I have
Oh,
to
it's
verify
three
the
set, right?
truthfulness of all the clauses.
Right,
Is
it's
it
three set.
only one clause?
No, it is three set, right? So the
Yes.
formula is a CNF formula. So it looks like C1 and C2 and C3 and C4 and so on. And you are given
Okay.
these C1, C2, 3, C3 explicitly.
Okay.
Yeah.
Okay.
So we are not, right now we are not interested in whether the formula would be satisfiable, whether the formula is satisfiable or not, but rather how many clauses will this procedure satisfy in expectation. Yeah. Okay, so so this is a problem that needs to be worked out, but would you like to take a guess, a random guess?
Hmm.
I mean, it's so completely fine if you don't want to guess, because this is something that we need to work out. Okay, so let's do that. So the answer is 7/8, and let's see why this is the answer. So suppose that the formula is so these are the M clauses of the formula. Okay. Now let xi be a random variable which is 1 if Ci is satisfied and 0 otherwise. Okay. So now, okay, can you tell me what is the quantity that we want to find if I have defined xi like this? So the quantity that we want to find is this, the expectation of sum over I xi. So are you this divided by the total number of clauses, but let's just work with this. So what is the question asking? It is asking us what is the expected number of clauses that would be satisfied. So that is exactly, so the number of clauses that would be satisfied is sum over I xi, right?
Yes.
So the expected value is just the expectation of that, right?
Yes.
So now let's look at this. Okay, so we know this, right? That this quantity do you know this? What is this called? This formula has a name. Yes, so it's called linearity of expectation.
Linearity of expectations.
Right. Yeah. So it basically says that the expectation function is a linear function. So expectation of a plus b is equal to expectation of a plus expectation of b. Okay, so
Yes.
now all we need to do is find each of these individual quantities and add them up. Okay. So fix ni. What is the probability that xi is equal to 1? So xi can only be 0 or 1. So let's find the probability that xi is 1. So xi is 1 when the clause ci is satisfied. Okay. Now suppose ci is x1 and x2 complement and x3. Then what is the probability that a random assignment would satisfy ci?
7 out of 8.
Right. Why?
Only when
Hello?
1 minus 1 by 8.
Right, that is 7 over 8. Yeah.
2 and then x3 is false. Only that assignment will
Right.
give us.
Right. So basically, no matter what clause you pick containing 3 distinct variables, there is exactly one assignment which cannot satisfy that clause. There are 8 assignments out of which only one does not satisfy the clause. So the probability that xi equals to 1 is 7 over 8. And since xi can only take the values 1 and 0, probability that xi is equal to 0 is 1 over 8. Now what is expected value of xi? It is by definition 0 times probability that xi is equal to 0 plus 1 times probability xi is equal to 1, and this is just 7 over 8. So basically this number is 7 over 8. So this number, let me write it down, therefore this number so this is the total number of clauses that can be satisfied in expectation, and we are interested in the fraction of clauses that would be satisfied in expectation. So we just divide this number by n and get 7 over 8. So is this fine with everyone?
Yes.
Yeah. So today we have quite a few such problems. We're going to work things out. So the next problem is also similar. So consider, let me switch the laser pointer. Consider the randomized algorithm for the 3-set problem mentioned in the previous question. However, so remember that, recall that in the previous question we had this guarantee that each and every clause would have 3 distinct variables. However, now I am removing that guarantee. So however, now the formula might contain clauses that do not have 3 distinct variables. In this case, what is the expected fraction of clauses that would be satisfied? And just a second, someone wants to join. Yeah. So okay, now that we have worked out the previous problem, would you like to guess the answer to this one? And is the question clear?
Yeah, question is clear, but
Right. Yeah, again, this needs to be worked out.
yes.
Yeah. Okay, so the answer is 1 over 2. Okay, so the answer is, okay, at least 1 over 2. At least 1 over 2 would be satisfied. Yeah. Okay, so before we move on to the proof of this, let's carefully look at the proof of the previous question. So over there, we got 7 over 8. Okay, the answer was 7 over 8. Where did we get that from? That was obtained by dividing this quantity by m. And so where did the 7 over 8 over here come from? It came from the fact that the expectation of xi was 7 over 8. And the expectation over here came from the fact that the probability of xi was 7 over 8, right? So suppose that this probability was p. Then what would the answer have been? Is my question clear?
Yeah.
Can you repeat? Yeah.
S-
So if this
So P
quantity over here were p, what would the answer have been?
P by M.
P.
Sorry,
No,
M,
p, right?
PM.
It would be p times m divided by m, so p, right?
Yeah.
Okay, so all we need to do to solve the fourth problem is find the p in the new case, right?
Mhm.
Is everyone convinced about this?
Yes.
Okay. So suppose that let xi be the same as before. Okay, we want to find and the answer is also p. Okay, so let's find this. Now there are three cases, okay? Fix an I. So what's the first case? The clause Ci has three distinct variables. So in this case, we just saw what probability of xi equals to 1 is, right? This is just 7 over 8. This is just from the previous question, right?
Yes.
The second is this. Ci has two distinct variables. So in this case, what would this probability be? So would you like to guess what this probability would be in this case?
3 over 4. Right?
At least 3 over 4. Why? Because the clause can look something like this, right? x1 or x1 complement and or x2, right? In this case, the clause is always satisfiable. So at least 3 over 4, right?
Right.
Yeah. But you are right. We can make it 3 over 4 by doing a pre-processing step. Just go over the formula, remove all such clauses which are like which have three variables, which have like three literals but just two variables. That we can easily do this pre-processing in polynomial time. So yeah, if you want this greater than or equals to be an equality, we are also fine. Third case is this. So what's the probability in this case?
At least half.
Right. Why at least? Because you can have a clause that looks like x1 and x1 complement. So if you combine all of these three cases, what do you get? You get that probability of xi is equal to 1 is at least 1 over 2, right? So okay, so we weren't able to find p exactly, but we know that p is at least half. So the answer is at least half. So is everyone fine with this?
So did you take the sum of these three quantities here?
No, I did not take the
7.
sum. So there are each and every ci can be in one of these three cases, right?
Yes.
So expectation of so depending on ci, the expected value of xi would be 7 over 8, at least 3 over 4, or at least 1 over 2, right?
Yes.
So ultimately we are interested in this quantity, expected value of sum over
Okay.
I xi which is equal to sum over I, expected value of xi. Now in every case this would be greater than or equals to half, right? Because this, depending on I, this would be either 7 over 8 or 3 over 4 or 1 over 2, right?
Yes, yes.
So this is at least 1 over 2 times m. But we are this is a number of clauses that would be satisfied in expectation, but we are interested in the fraction of clauses. So divided by m, you get 1/2. Yeah, so the answer is at least 1/2. Okay, now you might be wondering, can we do better than 1/2? Well, no, because you can have a formula that looks like just x1 and x2 and x3 and x4 up to xn. This you would only be able to satisfy with probably 1/2, right? So this is sort of tight for at least one formula.
Yes.
Yeah. So is this clear? Then we can move to the next problem.
Yeah, so the speciality of this problem is that the value is greater than 1/2. Otherwise, we could have flipped the coin and get the answer that whether the formula is satisfiable or not with the probability of half.
Oh no, but okay, so if you just flip a coin and output 1 or 0, then you might go terribly wrong, right? Because a formula might be like not satisfied. Let's say you have a contradiction, a formula that's not satisfiable at all. You flip a coin and it, like, there is at least half probability of it landing heads, right?
So half of the time the result would be correct, that the formula is not satisfiable.
Right. But the other half you would be totally wrong. So
half of the time it would be incorrect. Even if we work with a contradiction,
right,
half of the time the flipping of the coin will result into the correct value.
Right. Okay, so suppose you have that algorithm, right? But the question is, can you use it anywhere, or is that algorithm any good? Like,
so yeah.
I mean, it's an algorithm, sure, but look at what guarantee is it's giving. Like when it says yes, it's true with at most half probability. When it says no, it's again true with at most half probability, right?
Yes.
Yeah. So it's not doing you any good, right?
Yeah.
Yeah. On the other hand, the algorithm that we are looking over here does do you some good, because okay, you can't satisfy all of the clauses, but you can satisfy at least half of the clauses, right? Now these clauses can represent some real world constraints, right? For example, you want to invite guests to a party. Some guests don't want to come with the others, and so on, right? At least this tells you that okay, you can't make everyone happy, but at least you can satisfy half of the clauses, so you can make some people happy.
Yes.
Yeah. Okay, so if there are no more questions, we can move to the next problem. So which of the following statements is or are known to be true as per the current understanding, and we are supposed to select all that apply. RP is in NP, RP is in co-NP, co-RP is in NP, and co-RP is in co-NP. So would you like to guess?
So I think that the answers 1A and D are correct.
Okay.
RP is a subset of NP and co-RP is a subset of co-NP, and I'm not sure of the remaining two options. Probably they are not correct.
Okay, so you are right. A and D are correct, and we don't know anything about B and C, whether they are correct or not. Okay, so you might have seen these statements in class. Let's quickly prove this. Okay, so let's first try to prove the first statement. Why can't I go next? Oh yeah. So L is in, yeah. You were saying something?
First has to be correct because RP deals with the randomness, and whereas the NP deals with the non-determinism.
Right.
And in any case, the non-determinism would be more powerful than the merely something which is random. So therefore,
right. Yeah. So in this proof, we are going to exactly formalize that idea that random, like non-determinism, is at least as strong as randomization. Okay.
Yes.
Yeah. So let's pick a language L in RP. So L is in RP implies that there exists a polynomial time probabilistic Turing machine M such that X is in L implies probability that mx equals to 1 is at least half, and x is not in L implies probability mx equals to 1 is exactly 0. Okay. So this is just a definition of RP. Now what does this definition mean in terms of the computational graph? So what does this mean? Probability mx equals to 1 is greater than or equal to half. It means that at least half of the paths in the computational graph are accepting paths. Are you okay with this statement?
Yes.
Right. So x is in L implies at least half of the paths in the computational graph of M are accepting paths. And x not in L implies no path in the computational graph of M is an accepting path.
Yes.
Okay. Now consider a Turing machine N, which is exactly the same as M, but whenever M makes a random decision, N makes a non-deterministic decision. Okay. So is the definition of N clear?
Yes.
Right. Now N is clearly a non-deterministic Turing machine, and it runs in polynomial time. I also claim that it decides L. Why? Because when do we say that a non-deterministic Turing machine decides L? Whenever x is in L implies there exists one path in the computational graph that leads to the accepting state, and whenever x is not in L, every path leads to the rejecting state, right?
Yes, and moreover, I've never seen that a simple class belonging to its complement, except in the case
NL
of the
covalent.
space complexity.
Right. Yeah. So okay, so what do we want for NP? We want x is in L implies there exists a path, right? What this gives us is much more than that. Not only that does there exist a path, at least half of the paths are accepting paths, right? And
Yes.
x is not in L implies no computational path exists. So this statement over here also satisfies the condition for the acceptance of NP, right? The acceptance conditions for the class NP, right?
Yes, yes.
So the claim that L decides, the claim that N decides L is correct, right?
Yes, because for NP we just require only one path.
Right,
one
but right over here we have many more paths, but we don't care.
Yes.
We just need one, right? Yeah. So L is in NP, and since this is true for any language L in RP, RP is in NP. Okay. Now using a very similar argument, you can also show that co-RP is in co-NP, but there is a much simpler way of doing it. Once you have established that RP is in RP is in NP, what do? You pick a language L in co-RP. We know that if L is in co-RP, then its complement is in RP. But because RP is in NP, this means that its complement is in NP, which means that the complement of the complement, which is the language itself, is in co-NP. So L in co-RP implies L in co-NP, and so co-RP is contained in co-NP. Yeah.
Yes, so when we take the complement, then what is the universe of the discourse here?
0, 1 star. The set of all strings.
Okay.
Yeah. That is generally almost always the case, right? Yeah. So this is fine. We'll move to the next problem. So it's sort of a recall question. From the given statements, select the one with the correct order of inclusions as per the current understanding. The first option is RP is contained in BPP is contained in ZPP. RP is contained in ZPP, which is contained in BPP. The third option is BPP is contained in ZPP, which is contained in RP. Fourth option is ZPP is contained in RP, which is contained in BPP. The fifth option is ZPP is contained in BPP, which is contained in RP. The last option is BPP is contained in RP, which is contained in ZPP. So what's the answer to this one?
Option D.
D
Yeah.
option.
ZPP is contained in RP is contained in BPP. This is just a recall question. There is nothing to explain over here. So the next question is, assuming that P equals BPP, which of the following statements will be true? And select all that apply. P equals to RP, P equals to co-RP, P equals to ZPP, and P equals to NP. So what's the answer to this one?
So all the classes related to randomness will become equal.
Right.
and we can't say anything about this P is equal to NP
Right.
stuff.
Yeah. And the reason is that we know that P is contained in ZPP, ZPP is contained in RP, and RP is contained in BPP. So if P and BPP are the same, then all these three must be equalities. So in particular, P equals ZPP, and P equals ZPP equals RP, so P equals RP. So this first statement gives you A and C, and we also know that P is contained in ZPP, which is contained in co-RP, which is contained in BPP. So again, if these two are equal, all these three must be equalities. So you have P equals co-RP, which gives you B. But as of now, we don't know anything about what are the implications of P equals to BPP on the P equals to NP question. So we can't say anything about the option B. Yeah. So the next problem is, which of the below complexity classes are closed under complement as per the current understanding? Select all that apply: RP, co-RP, BPP and ZPP. So what's the answer to this one?
Maybe ZPP.
Okay, ZPP is certainly true, but so is BPP.
Yes.
Yeah. So okay. And first of all, let's just comment on these two. So the RP versus co-RP question is an open problem. So we can't say anything about the first two classes. And
Is this because that in case of RP and co-RP, we do have only one-sided error.
right, and
So,
the error is sort of
so
in the
therefore,
opposite
they are
direction.
unbounded at one end, so
Right,
cannot be closed under complement. And where is the remaining two cases? It's a two-sided error. So
right,
therefore, may
yes,
become closed under
right.
complement.
Yeah. So let's first prove it for BPP. Okay. So pick a language L in BPP. What do we have? What guarantee do we have? We have we have that there exists a polynomial time probabilistic Turing machine M satisfying X is in L implies the probability of acceptance is at least 2/3, and X is not in L implies probability of acceptance is at most 1/3. Okay. Now what I'm going to do is I'm just going to rewrite these two statements in the next slide. So X in L implies probability of rejection is at most 1/3, and X is not in L implies probability of rejection is at least 2/3. So is it clear how we arrived at these two statements from these two statements?
Yes,
Right,
we took their negation.
right. And we use the fact that MX has just two outputs, 1 and 0. So that's how we get these two statements. Now, what are we going to do? We are going to flip. So consider a probabilistic Turing machine M prime that flips the output of M. Now clearly M time is a polynomial time probabilistic Turing machine, and what guarantees do we have for M prime? There's a typo over here. This should be M prime. Yeah, sorry about that. So what guarantees do we have for M prime? X is in L implies probability of M prime X equals to 1 is at most 1/3. Why? Because when X is in L, probability that Mx equals 0 is at most 1/3, and whenever Mx equals to 0, M prime X equals 1. So we use this statement to obtain this statement. Similarly, when X is not in L, probability that M prime X equals to 1 is at least 2/3. Why? Because M prime X equals to 1 if and only if Mx equals to 0. So we use this statement to obtain this statement. So is it okay? Like, how do we get these two statements?
Yes, and does it have anything to do with the BPP class?
Okay, so BPP is closer to the complement, right? So co-BPP and BPP are the same. So that's why we don't have the class co-BPP.
Right.
Right. Yeah. So we obtained these two things. Now, okay. Again, what I'm going to do is I'm going to just rewrite these two statements. So what do we have over here? If X is in L, then the probability of acceptance is at most 1/3, which means that if X is not in L complement, then the probability of acceptance is at most 1/3. Similarly, over the second statement, we have that if X is not in L, then probability of acceptance is at least 2/3, which means that if X is in L complement, then the probability of acceptance is at least 2/3. Now the machine M prime is exactly the BPP machine for the language L complement, right?
Yes.
So L complement is in BPP. So is this fine?
Yes.
Okay.
Yep.
Yeah. So now we can do this. We can do a similar thing for ZPP. So if L is in ZPP, there exists a polynomial time probabilistic Turing machine M, which can output 1, 0 or fail. What guarantees do we have? We have that probability mx equals to fail is at most 1/2. Whenever mx outputs 1, x is always in L, and whenever mx outputs 0, x is always not in L. Now over here we would like to flip, but we have to be a little careful because we don't only have 0 and 1, we also have fail. So we have to somehow handle fail while flipping. So what we'll do is the following. Let M prime be a probabilistic Turing machine that flips the output of M only when it is 0 or 1. And if the output is fail, it leaves it as it is. It doesn't touch it at all. And what guarantees do we have for M prime? Probability that M prime x equals to fail is at most 1/2. Why? Because M prime x fails if and only if Mx fails. And this probability is at most 1/2. Then what about when M prime x equals 1? So when M prime x equals 1, we know that Mx equals 0, but Mx equals 0 implies x is not in L x is in L complement, that is x is not in L. So we have that whenever M prime x outputs 1, x is not in L, that is x is in L complement. Similarly, whenever M prime x outputs 0, Mx outputs 1 and therefore x is in L and therefore x is not in L complement. So whenever Mx equals to 0, whenever M prime x equals to 0, x is in L complement, and whenever M prime x equals to 0, x is not in L complement. So M prime x is exactly the ZPP machine that for the language L complement, right?
Yes.
And it clearly also runs in like polynomial time because we are just flipping the output of M. So hence L complement is also in ZPP. So is this fine? The idea over here was exactly the same as the idea in the previous proof. We just had to handle fail carefully.
So what was the problem formulation of this problem? What was the question?
Because the question was which of the below complexity classes are closed in a complement. So
yes, so we didn't know anything about RP and the co-RP.
Right, okay, so the RP versus co-RP is an open problem. So if RP is closed under complement, L is in RP implies L is in co-RP, and then you can prove that this implies co-RP is equal to RP.
Yes, so because RP is open at one end and
Right.
co-RP is also open at another end. So
Right.
therefore, is this because that the ZPPP is equal to the RP intersection and then the co-RP? Because in that case, both the ends will get filled.
Right.
So maybe because
Yeah, so basically what would happen is if you try to replicate these proofs for RP and co-RP, whenever you try to flip, you won't get the exact inequalities that you want.
what if I take the intersection of something, say RP and the co-RP? Would it be totally phi or would it be
No,
null?
RP intersection co-RP is, we know something about what RP intersection co-RP is, right? It's exactly ZPP.
We do not know anything.
No, we know that RP intersection co-RP is ZPP. We don't know whether they're equal or not. So what?
Yes.
Right,
Yes.
yeah.
Okay. Now I understood.
Yeah. Okay, so notice over here that okay, so we have been looking at flips for quite some time, right? So we saw that you can flip the output of a deterministic Turing machine. We saw that you cannot flip the output, at least it is not clear to us right now how to flip the output of a non-deterministic Turing machine. For here we saw that you can flip the output of a probabilistic Turing machine. But we also saw that there are some relationships between probabilistic Turing machines and non-deterministic Turing machines, right? Basically, in probabilistic Turing machines, you have two transition functions. You choose one randomly. In non-deterministic Turing machines, you have two transition functions. You choose one arbitrarily. So there are some connections between randomized Turing machines or probabilistic Turing machines and non-deterministic Turing machines. However, over here we saw that you can flip the output of the probabilistic Turing machines. Okay, so just try to think why this is the case. Yeah.
So I have a query here that what if the output of a PTM, probabilistic Turing machine, is decided through the outcome of a dice instead of the flipping of a coin. Let us say if instead of two, if we have the six different possibilities,
Okay.
then would we still be able to flip the outputs?
Okay, so you can basically, so you are flipping a die, you are throwing a die, right? So you have six possibilities. You can sort
Yes.
of reduce that to throwing, like tossing a coin. How? Toss a coin three times. So
Would it be same?
that gives you eight possibilities. Throw away two possibilities.
Mhm.
So basically, you just throw away two possibilities.
So I am doubtful here that it is true that we can convert every tree, every general tree into a binary tree. It's possible. We do
Okay,
have mechanism to convert that. So possibly that if the outcome is determined through the throwing of a dice, probably it can be or equivalent tree can be constructed, wherein the outcome is determined through the flipping of the coins. But then, would the flipping of the outcome be still possible?
okay. So when you say that you are using a die, okay, so when you say that the outcome depends on the throwing of a die, what do you mean? You mean that whenever the Turing machine wants to make a random choice, it throws a
Yes.
die, looks at the choice, and what does it do then? It Are you saying that there are six transition functions, and it picks
Yes.
from one of those six functions?
Yes.
Okay, so at the I think beginning of the course you would have seen that uh, why we are only taking two transition functions for non-deterministic Turing machines, right? You might have seen that if you have multiple transition functions, you can always reduce that in the case of two transition functions.
So I don't remember it. Probably there might be some reason behind it,
Okay, so
but I
okay,
don't
so
recall.
what do we know?
Level.
What do we know for non-deterministic Turing machines is the following: the model where users have two transition functions can simulate models where you have constantly many transition functions. And basically, if you basically almost exactly the same proof works in this case as well.
Okay,
Yeah.
fine.
So basically, you have six functions, right? What you would do is you would like create eight functions, two of which are dummy, and
Hmm.
then once you have eight functions, you can again flip a coin three times, right? Yeah.
Yes. So we would be doing some kind of the boosting here at the most.
Right. I think yeah. In the worst case, you might yeah. The worst case, the probability would be some 1 over some constant, and you can boost it.
Yes.
Yeah.
Yes. Yes. Yes.
But again,
Clear.
it depends on how you define all the probabilities, because if you define them just right enough, you might also get half as well.
Yes.
Yeah.
Yes.
For example, you have six transition functions, but the first three and the last three are the same. So it's just throwing it like flipping a coin, right?
Hmm.
Yeah. So yeah. So you may or may not do boosting depending on how you do things.
Yes.
Yeah.
Yes. I understood.
Right. Yeah, so then let's look at the next problem. So next problem is consider the following algorithm for three colorability. Each of the vertices are assigned one of the three colors red, blue or green independently at random. And after the colors are assigned, it is checked if the color assignment constitutes a proper three coloring. The algorithm, the algorithm declares that the graph is three colorable if the assignment is a proper three coloring. Otherwise, it declares that the graph is not three colorable. Now select the correct option. The options are: the algorithm always reports the correct answer, the algorithm may report false positives but does not report false negatives, the algorithm may report false negatives but does not report false positives, the algorithm may report false positives and false negatives, and this algorithm never reports the correct answer. So would you like to guess the answer to this one?
So
See,
see, yeah, it may report false negative.
Okay, yeah. Yeah. So that's the answer, and let's see why. So the first option is the algorithm always reports a correct answer. Okay, that's neat. That need not be true, right? Because the graph might be three colorable, but you picked a random three coloring, and that might not be a valid coloring, right?
Yes.
So the first option is clearly incorrect. Now let's look at the second option. The second option is this algorithm may report false positives. So let's look at just the first part of this option first. Okay, so what do we mean by a false positive? So first of all, what is a positive for us in this case? A graph which is three colorable, right? That is a positive,
Yes.
right? So that's a positive instance. And what does a false positive mean? A false positive means that a negative, that an instance which is not positive, that is an instance which is negative, is being reported as a positive instance by our algorithm, right? So in this case, it would mean that a graph which is not 3 colorable is being reported as a 3 colorable graph by our algorithm. But notice that that would never happen because of this check that is performed. So we are taking a random coloring, checking if it's 3 colorable, it's a valid coloring or not, right? So if the graph is not 3 colorable, no coloring would be a valid 3 coloring. So a random coloring also won't be a valid 3 coloring, right? So this check would ensure that you do not have any false positives. Is this fine?
Yes.
Yeah. Okay, so this algorithm may report false positives. So we know that this algorithm does not report false positives. So that immediately rules out option D, because it may report both false positives and false negatives. We know that it does not report false positives. So D is A, B and D are not correct. And the option E is the algorithm never reports the correct answer. Well, you might get lucky and pick the right 3 coloring. So that sometimes algorithm might report the correct answer, right? So E is also not correct. So are you convinced that A, B, D and E are not correct?
Yes.
Right, now the only remaining option is C. Let's see why that is correct. So this algorithm may report false negatives but does not report false positives. You have already seen that this part of the statement is correct, right?
Yes.
Yeah. So now we only need to show that this is also correct. Okay. What is a false negative? In our case, a false negative would be a 3 colorable graph, which our algorithm reports as not being 3 colorable. Are you convinced about this?
Yes.
Right. Now, notice that this can obviously happen. Why? Because let's say out of all the possible 3 colorings, out of all the exponentially many possible 3 colorings, only one is valid, right? Now, with very high probability, when you pick a random coloring, you won't pick that coloring, right? So with very high probability, you might pick the wrong coloring. So this check will fail, and you would say that okay, no, the graph is not 3 colorable. So yes, you can say that you might report that a 3 colorable graph is not 3 colorable. This algorithm might do that. So the algorithm does report false negatives. Is this fine?
Yes.
Yeah. So now let's look at the next problem.
And this problem would there be in RP because in case of RP we can have false positive, but we cannot have false negative. So this is in co-RP probably.
Oh no, wait. This is okay. So first of all, this problem is NP complete, right?
Yes, 3 colorabilities in.
Right. So if it were in RP, what would that mean?
So the meaning is that so in case of RP, since the probability, if X belongs to the language and the value of the probability is greater than half, so we are not sure about the positiveness. So it may result into the false positive.
No. So what I'm
So
asking
in case
is,
of the co-RP, we won't be getting the false positive, but then we may get false negatives, right?
okay, no, so what I'm saying is, suppose this were in RP, so suppose this problem were either in RP or in co-RP. This would immediately
Yes.
imply something about the NP versus RP question or NP versus co-RP question, which are open problems right now.
Is okay.
Yeah, so this is neither in RP not in so okay, because of the current algorithm, okay, let me put it like this. The current algorithm does not imply that this is in RP, nor does it imply that this is in co-RP. Why? Okay, so RP and co-RP are there is a little more to RP and co-RP than false positives and false negatives. This one
Yes.
more constraint.
Okay.
What is that?
So the constraint is that whether the non-determinism is as powerful as the randomness or not.
No. Okay, so if you look at the definition of RP and co-RP,
Yes.
you have something more than just false positives and false negatives. There are like some probabilities over there, right?
Yes.
Now, for the example that I gave, a graph where only one coloring is valid. Okay.
Yes.
So what would this algorithm do for that? How would this algorithm perform? So you pick a random 3 coloring. The probability of picking that coloring is exponentially small, right?
Yes.
So the success probability of this algorithm is exponentially small, right?
Mhm.
But you need it to be at least half. Now, okay, you might think, let's boost it. However, if so, here's the general rule of thumb, and it's certainly true in this case. If the success probability is 1 over f of n, you would need like f of n amount of time to boost it, right? So if the success probability is inverse exponential, you would need exponential time for the boosting to work. But in that case, your randomized Turing machine, which uses boosting, would no longer be polynomial time, right? So because of this very tiny success probability of this algorithm, this does not imply anything about this being in INP, this being in RP or co-RP.
So I have a related query here that
Right.
in case of NTM, if I give input to the NTM, then every time I would be getting the same output.
Right.
Now, in the case of the PTM, for the same input in the different iteration of the executions, is it possible that I get different outputs?
Yes. In fact, you would definitely get different outputs.
Okay.
But what guarantee do you have? So you know that, okay, let's just take the example of the RP machine, a machine that decides the language in RP, okay. Okay, so, and suppose that X is in the language. And what guarantee do we have? The probability of the machine outputting 1 or machine accepting is at least half, right?
Yes.
So if you execute the machine on the same output a lot of times, what would happen?
Yes, so gradually, so it will decrease this time.
Right. Okay. No. Yeah. So at least half of those machine. Let's say you execute the machine 10 times. Then okay, 10 is very small number. Let's say 1,000,000 times. Okay.
Yes.
Then approximately 500,000 times, the machine would have outputted 1.
Yes.
So okay, you are right. Like between different iterations of the algorithm on the same input, you might get different results, but you have the statistical guarantee that if you do it many more times, then you would roughly converge to that number, the number that you have in the probability.
Yes.
Yeah.
Yes.
And that's basically what we are using in boosting, right?
Yes. Yes.
Yeah.
Yes.
So let's look at the last problem for today. So consider the algorithm for 3 colorability from the previous question. So pick a random 3 coloring, check if it's valid or not. If it's valid, say the graph is 3 colorable. If it's not valid, say the graph is not 3 colorable. Okay. Now select the correct option. The algorithm always runs in polynomial time. The algorithm sometimes runs in polynomial time, but may not always run in polynomial time. However, the expected running time of the algorithm is polynomial. The algorithm sometimes runs in polynomial time, but may not always run in polynomial time, and the expected running time also need not be a polynomial. And the algorithm never runs in polynomial time. So, would you like to guess which answer is correct?
So I think the answer C is correct.
Okay.
Because sometimes it may run in the polynomial time. It's not necessary that every time it will run into the polynomial time. So polynomial, something is polynomial, something is non-polynomial. So the expected value obviously cannot be polynomial.
Okay, so let's look at the algorithm. What is it doing? It is first of all picking a random 3 coloring, right?
Yes. Yes.
And then it is checking if that 3 coloring is valid or not. These are the only 2 operations the algorithm is performing, right?
Yes.
Okay. Now, how much time would I need to pick a random 3 coloring?
How much time?
Right.
So constant, constant amount of the time is required. For the 3 coloring, if I have been picking say n number of the vertices, then NC3. So yeah.
No. Okay, we are supposed to pick a random 3 coloring. So here's how we do it. So okay, let me go to the previous question. Yeah. So each of the vertices are assigned one of the 3 colors, red, blue, or green, independently at random.
Yes.
Okay, so you just need to pick one of the 3 numbers, 0, 1, or 1, 2, and 3. So you need to pick from one of these 3 numbers independently at random. Okay.
And how, assuming that there are n number of the vertices, so
right.
for every vertex we would be making 3 choices, 1 out of 3.
Right. Okay. So okay, let's forget all the vertices. Let's just look at one vertex right now. Okay. For that vertex, we just need to make this random choice, right? Which we do in constant time.
Correct.
So if there are n vertices and we are doing it for all of them independently, right? So for one
Yes.
vertex you need constant time, for n vertices you need constant times n time.
So then we won't be making choices independently, because
No,
once I
no,
assign color to a vertex, then obviously based on that assignment, I shall be making another
no, 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 no,
choice.
no, no. So what the algorithm is doing is the following: it picked the first vertex, picked a color for it, forgot it, picked the second vertex, again picked a
Okay.
color for it, right? Because it's doing it independently, right?
Yes.
Right. So basically, the first operation, picking this random coloring, happens in polynomial time.
Yes.
Okay. Now, what about the second operation? Checking whether the picked coloring is valid or not.
So for this, we require the polynomial amount of the time here.
Right, because three colorability is an NP, right?
Yes.
So both the operations are polynomial time. So the algorithm always runs in polynomial time.
Correct.
Yeah, okay. You might be saying, okay, this is a NP complete problem. You have a randomized polynomial time algorithm. Something is wrong. Yes, the success probability is very bad.
Yes.
Right.
Yes. Yes. Because the algorithm is designed in this way.
Right.